Swayam Prabha. Digital India. Educated India.
A warm welcome to the 6th lecture on the subject of digital signal processing and its applications. We take up today a further discussion on the properties of systems that we had embarked upon in the previous lecture. All right, so let's once again put down a few thoughts that we had come up with in the previous lecture. So, in the previous lecture, we had essentially looked at linearity and shift invariance. And we had seen that linearity comprises of two properties, additivity and homogeneity. In fact, we had defined additivity and homogeneity by using special cases of linearity. So, we had defined them as properties which were subsets of the properties of linearity. However, we had remarked and I had left it to you as an exercise to prove that the relationship is two-way. In other words, additivity and homogeneity together come to make linearity once again. That means together they are sufficient for linearity to hold. So, it is both ways. We had also looked at shift invariance. And I might remark that when we are very clear that the independent variable is time, then shift invariance is sometimes called time invariance. So, in many texts or in many references, we encounter the term time invariance, and the meaning is shift invariance with the independent variable being time. Now, we also explained the context from which these properties arose. The context was that we were trying ultimately to insist or realize a property of behavior with respect to rotating complex numbers of phasors, and ultimately we were trying to insist on certain properties pertaining to the response to sinusoidal excitation. And we explained why that was the case. That was because sinusoids are not only found in nature, at least in an electrical context, but they are also very smooth functions. Now, what we intend to do today, first is to continue what we had just embarked upon in the previous lecture, namely to look at a linear shift invariant system and to characterize it completely. We had remarked in the previous lecture that a linear shift invariant system, and now we will use an abbreviation for this. So, a linear shift invariant system is completely characterized by its response to a unit impulse delta n. You see, we had agreed that we would use essentially 3 steps in this proof, and we also agreed on what we mean by characterization. We had also cautioned ourselves that we should not bring in more than we have put in the definition right now. Right now in the definition we have not brought in any sine waves, or we have not brought any rotating complex numbers, we have brought in no system functions or transfer functions. We only have the knowledge that there is a relation between the input and the output, and that relationship obeys the properties of linearity and shift invariance. With this, we must now prove that if I know the response to one particular input, namely the unit impulse, I know everything about the system. In other words, I know the output that would appear for any input, and that is what we are now going to prove. Well, the first step in the proof is to observe that one can express any input in terms of the unit impulse, and that is very easy to see. So, let us take an arbitrary example of an input. So, at 0 let the input take the value 5, at 1 let it take the value minus 2, at 2 let it take the value 3, and for the moment let us not confuse matters, we will not worry about what is present at 2, 3, 4 and so on after and beyond 2. At minus 1 let it take the value 4, at minus 2 let it take the value let us say minus 5, and then let it do whatever it wants to after that. And we will show that if we focus our attention on this part between minus 2 and plus 2, we can express this as a combination of appropriately shifted unit impulses, shifted and scaled. So, you see it is very easy to see that this sample at 0 can be obtained by putting a unit impulse here and multiplying it by 5. So, this can be contributed by what is called 5 times delta n. So, let me write that down. In fact, let me take any other specific point. So, let us take the point n equal to 2. The point at n equal to 2 can be contributed by shifting the impulse to 2, in other words writing delta n minus 2 and multiplying it by 3. So, this is contributed by 3 delta n minus 2, and similarly this is contributed by minus 2 delta n minus 1, essentially the unit impulse shifted forward by 1. If the unit impulse is shifted backward by 1, you would put an impulse here, and if you multiplied it by 4, then you would get this sample, and similarly for this and similarly for any other. So, we make the remark that this xn can be written as well many other things together with minus 5 delta n plus 2 plus 4 delta n plus 1 plus 5 delta n minus 2 delta n minus 1 plus 3 delta n minus 2 and of course many other things. Right. In fact, we can now come up with a more general expression here. If we notice, a typical term in this summation is really the sample value at a point k multiplied by an impulse, a unit impulse shifted by that k. So, for example, this is the term for k equal to 0, this is the term for k equal to 1, this is the term for k equal to minus 1 and so on and so forth. So, we have in general xn being a combination of delta n minus k for all integer k and the coefficient in the linear combination is x of k. Now, although it is very easy to understand this, particularly because we have just taken an example, one must also appreciate some finer points in this discussion. The finer point is that x of k in this discussion is now a constant, it is not a sequence for any particular k. Secondly, delta of n minus k is a sequence, not a constant. Although it has only one sample, it is a sequence, right. So, what we are saying is that a given input, any given input, can be thought of as a combination of several sequences, each of which have only one sample. These finer points must be understood because they are important in the proof. I must repeat that if there are any questions on the way, you must ask them then and there. Do not wait until the discussion is done to ask questions. So, if there are any questions at any point in time, you must raise your hand right there and ask the questions. So, what we are saying in effect is that x of n, the whole sequence xn, is a summation over all integer k, xk delta n minus k. Note, this is a constant, this is a sequence, and we assume that when we put delta n into this LSI system, we get a sequence Hn emerging as the output. So, here there is a sequence that goes in and a sequence that comes out, please note. Naturally, this is the unit impulse response, the response of the system to a unit impulse. Now, we first invoke the property of shift invariance. So, shift invariance tells us that if I were to give delta n minus k for a fixed k in place of delta n, the only result on the output would be a shift of the same k, and therefore, if delta n produces let us denote the system by S now. If delta n produces Hn, then delta n minus k is going to produce H of n minus k. That does half our work. So, here we have invoked shift invariance. We now invoke homogeneity. Xk times delta n minus k. Remember, xk is a constant. Xk times delta n minus k, when applied to the same system, is therefore expected to produce xk times Hn minus k. Note again here, h of n minus k is a sequence, xk is a constant. The interpretation must be very clear at every step. So, here we have invoked homogeneity or scaling. And finally, we invoke additivity. Now, additivity says summation over all k, what we are saying is invoke additivity pair by pair notionally. Keep taking pairs and go on constructing the whole sum here, right. So, summation k over all integers xk delta n minus k would then be expected to produce summation xk Hn minus k. And in fact, this is really the output yn because this is the input xn. And what is significant is that here we have put no restriction on xn at all. For any arbitrary xn that we gave, we have an expression for the output in terms of the impulse response Hn and the input xn. So, in fact, not only have we proved the theorem, but we have also given what is called a constructive proof, a constructive as against an existential proof. I must distinguish, in some situations one can only give an existential proof, that means one can prove that a certain solution exists, but it is not easy to construct the solution, or the proof itself provides not much of a cue on how one might construct the solution. But here we are fortunate to have a proof that is not just existential but constructive, in that it actually gives you a process for construction of the output given the input and the impulse response. In fact, what we have even now is the construction in a rather raw form, in the sense that we have what seems like a fairly complicated expression. Let us spend a few minutes in interpreting what we have got. So, let us first draw a couple of conclusions. So, conclusion is that the theorem is proved and the proof is constructive, in that you can actually explicitly write the output in terms of the input and the impulse response. And when we write it like this, the interpretation is very easy. What we are saying here is, essentially the output is a linear combination of several shifted versions of the impulse response. The impulse response shifted by k samples, weighted by the input sample at the point k, and then added over all such k. That is what the output is. So, you can visualize this. You can visualize that if the system were to respond to a unit impulse with a sequence Hn, and what you have is the output is essentially this sequence Hn shifted by all possible shifts, and the particular shift by k is multiplied by the input sample at the point k, and all such shifts are added together. This is one interpretation. So, here we conceive of the output as a sum of many shifted impulse responses. That is one way to look at it. But often that is not what we want to do. We do not want to sit and put so many sequences down and add them. We would much rather find out the output point by point, and for that we need to carry out a little more work on the expression that we have just got. Therefore, we will introduce some terminology now. You see, this output yn has been obtained by an operation between the input sequence and the impulse response sequence here, and we will give that operation a name. It is an operation not between two numbers, but between two sequences. So, we are saying that the output sequence some operation is obtained by some operation acting on the input sequence and the impulse response sequence. It is an operation between two sequences. And therefore, let me underline sequence everywhere. It is an operation between two sequences. We will give this operation a name. We will call this operation convolution, and there is a reason why we give it that name. You see, we typically use the term convoluted in common discussions or in colloquial terms, where something is complicated or where something twists and mixes. You know, one sometimes refers to a convoluted argument to denote a set of statements or a set of utterances or a set of justifications which are very complicated to understand and which intertwine together in some complicated way and perhaps lead to a conclusion, but it is not at all straightforward to see how they start from the beginning and come to a conclusion. We say it is a very convoluted argument. right. Convoluted in general tends to refer to twisting and mixing together in a highly intertwined, in a highly interactive way. And in a minute we will see that that's exactly what we are doing in a way between the input and the impulse response here. If you think of the input as a string of samples, and if you think of the impulse response as a string of samples, what we are doing is to intertwine those strings together in a very complicated and a very fine manner to obtain the output. Yes, there is a question. Yeah, so the question is that should we be writing the operation between the input sequence and unit impulse response sequence? Well, the answer is yes. We have sort of ignored the word unit, but we will write that to be clear here. So, it is the response to a unit impulse, that is correct. One should, in a way, one should emphasize that it is the response to a unit impulse, because otherwise, it could be a scaled impulse too. Now, we will try and understand both of these interpretations with a specific example. We will take a very simple input sequence and a very simple unit impulse response sequence. So, we will take the input sequence and here I am going to introduce some notation once again for convenience. When we have a very short input, an input which is non-zero only for a few samples, we tend to use this notation, where we denote the location of one of the points and then we denote all the other points around it. So, we indicate it, for example, by showing that at point 0, I have the sample, let us say 6 here, and then I have 1, -1 and 2. Obviously, 1 occurs at the point n equal to 1, -1 at the point n equal to 2, and 2 at the point n equal to -1. Needless to say, just for the sake of notation, I am trying to explain this notation. This is the same thing as writing, or it is the same thing as writing, all of them are the same. So, we can write them in any manner that we please. But what is important is to mark one point and all other points follow from there. Yes. So, here the question is, you see the sequence is 2, 6, 1, -1 respectively at the points -1, 0, 1 and 2. Okay. So, therefore, you could say that this sequence takes the value 1 at the point n equal to 1 and the other marks of course follow, and similarly it could be marked at -1 and the other points obviously follow. Yes. So, similarly, let us take a very simple impulse response, of course a unit impulse response if you please, but henceforth when we say impulse response we will mean the unit impulse response. We will not want to keep repeating unit every time. The unit impulse response, the impulse response is very simple. It is just 1 and 1 respectively at 0 and 1. Now, I shall obtain the output in two different ways and we will explain therefore the operation of convolution, why it is called convolution. One way, as I said, is to use this expression with the interpretation that you are shifting and adding the impulse response several times. So, what would this mean? This would mean I have taken the impulse response, I have shifted it by each k, I have scaled that shifted impulse response by the value of the input sample at the point k, and I have summed up all these shifted versions of the impulse response. So, let us sketch that out. Let me remind you of the input once again. What it would mean is I must shift the impulse response backward by 2, keep it as it is, shift it forward by 1, forward by 2 and respectively multiply by 2, 6, 1 and -1. So, here I am. So, x k h n minus k. So, k equal to, I will write k and I will write this sample here. So, k equal to minus 1 and I have 2 and this occurs at 0. K equal to 0 and I have 1 here. For convenience, I will put the 0 in at k equal to 1, I have, I am sorry. So, this should be multiplied by 6, that is 6 and 6, all right. So, let me complete this. So, 1 at k equal to 1, of course, I have 1 and 1 occurring at 1, and for k equal to 2, I have minus 1 at k equal to 2. So, these are the 4 x k h n minus k's, and now of course, I add them. So, I will have to let me draw it again, let me put them down since this is the first time we are solving such an example. We have 2, we have 6, 1, and we have minus 1. So, of course, and this is the point, I will mark it from above, this is the point 0 here. So, I have of course 2, 8, 7, 0 and minus 1. This is the output sequence y of n. Is that clear? Yes. Does everybody follow this? Any doubts on what is going on here? However, what is very clear from this example is that you can obtain the output point by point, unlike what we are doing here, where we are putting sequences and adding them up, by looking at what is expected at each point. You see, what I mean by that is, we reinterpret, and let us do that. We could also obtain yn point by point for each n. And here all that we need to do is to reinterpret the expression for convolution. So, what we are saying is, take note of the expression for convolution once again. And instead of now thinking of x of k as a constant and h of n minus k as a sequence, I told you the interpretation is important. We will think of both x of k and h of n minus k without the summation as sequences indexed by k. So, x k is a sequence indexed by k, that is easy to understand. H n minus k is also a sequence, now not indexed by n, but indexed by k. Okay. So, think of h of n. So, the difference in that approach is, think of h of n minus k as a sequence in k, not in n, for fixed n. You see, because you are trying to calculate point by point. And how do we obtain that sequence? We need to interpret that. So, towards interpreting that, we will follow 2 steps. We will first go from h k to h k plus n for a fixed n. And obviously for a fixed n, h of k plus n is essentially in the sequence h of k shifted backward by n. So h of k plus n is h of k shifted backward by n. And the next step is of course to replace k by minus k. So when we replace k by minus k, what we are doing is to reflect about k equal to 0. Replacing k by minus k essentially means switching every pair of points. For example, switching 1 and minus 1, switching 2 and minus 2, switching 3 and minus 3, keeping 0 where it is. So it really means you are making a mirror image of that sequence with the mirror placed at k equal to 0. Remember, the sequence that you are mirroring is h of k plus n. Alright. So we are mirroring h of k plus n, and we can now visualize what to expect. In fact, I don't need to take a specific example. We can write in general. In general, you know, when you have at 0 something, you might have h of 0 and so on, isn't it? H of 1, h of 2 and so on. This is the sequence here, h of minus 1 and can go on behind. If this is hk, then h of n minus k is going to be obtained by shifting this backwards. So maybe we'll first write h of n plus k, shifting this backwards. So this appears at minus n, and this can go on, and then reflection. Now when you reflect, minus n goes to plus n. H of 1, which appears here after minus n, will now appear before plus n. So what you do is move this to the point n and then switch or mirror all the points around that point n. Alright, so what we have is as follows. H of n minus k is therefore at n put h of 0, at n minus 1 put h of 1, h of 2 and so on behind, and here you have h of minus 1, h of minus 2, and this can go on. This was not too difficult to see generally, but we can of course fix our ideas by taking the same sequence that we did a minute ago for Hn, namely if we consider Hn as we did there, or you see of course here you can call it h of k if you like to be specific. And h of n minus k is essentially at n put 1, and then therefore at n minus 1 you will also have a 1. Simple. So essentially what we are saying is that this Hn or h of n minus k more precisely has a 0 at the has 1 at the point n and 1 at the point n minus 1, and therefore if a system had the impulse response given by this Hn, if an LSI system had this Hn as its impulse response, remember this tells me everything about the LSI system. Once I know this unit impulse response, I know everything about the LSI system. So once I write this, I have specified it completely. If I have an Xn, what I am saying is y of n is essentially x of n times 1 plus 1 times of x of n minus 1. So, the impulse response also gives me an interpretation of what the system does. In fact, more particularly a finite length impulse response immediately gives us an interpretation. The moment you have a finite length impulse response means an impulse response where the number of non-zero samples is finite. So, here for example, the number of non-zero samples in the impulse response is only 2. So, the beauty is that with this interpretation of the operation of convolution, I also have an interpretation for how the impulse response describes the system. For a finite length impulse response, it is very straightforward. It tells you that the output at any point becomes a linear combination of the input at that point and a few points around it. Now, the key issue is whether you involve only points from the so-called past or also points from the so-called future. I am saying so-called because past and future have a meaning when the independent variable is time, not otherwise. But if the independent variable is time, it is very easy to see that if the impulse response has non-zero samples for negative n, then you are going to involve so-called future samples. And if the impulse response has non-zero samples only for non-negative n, that is n equal to 0 and positive n, then the output at a given point depends only on the input at that point and on points before it, so to speak, points from the past, right. We will come to that a little later. But let us use this expression, let us use this idea to recalculate the output that we did a few minutes ago. So, there we had x of k given by 2, 6, 1 and minus 1, isn't it? And now you can visualize h of n minus k. So, I will just write it down on the side. You see, when I want to calculate, so h of n minus k look like this, 1, 1 at n. So, now I can recalculate yn using this very easily. You see, I can visualize that when n is minus 1, I can visualize this sequence being brought here, and the 1 comes in contact with 2. So, you multiply them pointwise. The 1 gets multiplied by 2, 2 plus this 1 gets multiplied by a 0. So, the output is 2 here. On the other hand, when n is 1, I am sorry, when n is 0, then this 1 clashes with a 6 and this one clashes with a 2, and therefore you have 6 plus 2, that is 8. Similarly, when n is 1, you have this one colliding with this one and this one with this 6. So, you have 7 there. And when n is 2, you have this one colliding with minus 1. So, the product is minus 1 and this collides with 1. So, you have 1 into minus 1 plus 1 into 1, that is 0. And finally, when n is 3, you have 1 colliding with a 0 and 1 colliding with a minus 1, and therefore, you have just a minus 1 there. For n less than minus 1, it is very easy to see that these two 1s collide only with zeros here. And for n greater than 3, it is very easy to see again that these two 1s collide only with zeros, and therefore, there is no non-zero sum at all. Now, it is convenient to give another mnemonic to this operation, and that mnemonic is to think of one sequence as being static and the other sequence as being dynamic here. You might think of this sequence as the passengers on a platform, and you might think of this sequence as the passengers inside the bogies of a train that moves. and you might visualize that this train moves one step at a time, and there is a handshake between the passengers on the platform and the passengers on the train. At every point, the output is interpretable as the net effect that the train feels due to this handshake, right. So, it is a combination, some passengers are stronger, some passengers weaker, you might think of that as the number put there. Of course, some passengers make a handshake outwards and some passengers make a handshake inwards. That is the positive and negative part of it. So, altogether at every point there is a net impact of all these handshakes, and the train moves one step at a time. And the net impact is interpreted as the product of the strength of the person inside with the strength of the person outside summed over all the passengers, which thus make a handshake. And of course, after some time you run out of passengers. Now, this is easy to understand when you have a finite number of passengers. The train has a finite number of passengers and the platform also has a finite number of passengers. But it is not too difficult for us to extend the idea to a context where the train has an infinite length and the number of passengers on the platform is also infinite. It takes just a little more visualization to arrive at an interpretation for that context. Is that right? So, this is another convenient mnemonic to interpret convolution. Is that right? Convolution is a very fundamental operation in the study of linear shift invariant systems. Convolution is an operation in its own right. What I mean by that is, other than the fact that it occurs in the context of linear shift invariant systems in a very, very meaningful way, you can think of it as an operation between two sequences independent of the context. What I mean by that is, you could have taken two sequences, multiplied them point by point to get an output sequence. That is also an operation between two sequences. You could have taken two sequences, added them point by point, and that gives me an operation between two sequences. Of course, those are what are called point operations. That means each point of the output involves only the particular point of the input and the particular point of the two sequences. If you add sequences point by point, then you are operating in a pointwise way. So, the output is a pointwise function of the input and the impulse response, or the output, if you do not want to call it them input and impulse response, if you have two sequences, the output is a pointwise function of the points of the two sequences. However, convolution is not a pointwise function. In convolution, we must now see from this example that in principle, all the points of the input and all the points of the impulse response have come into the picture to create a point of the output. Again, going back to the mnemonic of the train and the platform, the impact felt by the train at every move is dependent on all the passengers on the platform and all the passengers in the train. It is not passenger by passenger. Is that right? So, it is truly, convolution is truly an operation between two sequences and not pointwise at all. This must be emphasized and understood very clearly. So, are there any doubts before we proceed? It is a very important operation and we must be absolutely clear how this is done. Now, I put before you an exercise to do, and I also introduced the verb form of convolution. Convolution is a noun, it is the name of the operation. The verb form is convolve. So, convolve xn, which is 7 minus 4, 3, 6, 2 with hn given by 2 minus 3 minus 6, 0, and let me put another point there to make you work a little harder. So, I leave this for you as an exercise, obtain this convolution. And we conclude this lecture with this exercise and just give a feel of what we are going to do the next time as a trailer. The next time we are going to take note of this relation between the input, the impulse response and the output, and we are going to fulfill our first promise, namely the whole reason why we want to look at linearity and shift invariance was that if I gave a complex exponential as an input, I would have expected a complex exponential to emerge. But we said we need one more thing, that is stability. And the next lecture will begin by seeing what happens when we give a complex exponential as the input to an LSI system, and then see whether we are happy with the system being only LSI or we need something more. That would bring us to a few more properties that we desire of linear shift invariant system. Thank you.